What if I told you there's an American V8 that makes 505 horsepower, naturally aspirated, revs to 7,000 RPM, weighs less than most import tuner engines, and costs about as much as a nice set of golf clubs? Oh, and it's been bulletproof, reliable in everything from 200 Murphy Corvettes to 3,800-pound Camaros running flat out at racetracks for hours on end. This is the story of the LS7, the 7-liter monster that made European supercar engineers question everything they thought they knew about high-performance engines. Picture this. It's 2005, and if you want a naturally aspirated engine making 500-plus horsepower, you're looking at Ferrari, Lamborghini, or maybe Mercedes-AMG. These exotic power plants cost more than most people's houses and require PhD-level technicians just to change the oil. Ferrari's Enzo engine? That's a 6-liter V12 making 651 horsepower. Impressive, sure, but it costs $150,000 just for a rebuild. The Lamborghini Gallardo's V10? About 500 horsepower from 5 liters, and good luck finding parts when something breaks. Meanwhile, in a GM powertrain facility in Michigan, engineers were putting the finishing touches on something that would flip the entire high-performance engine world upside down. The LS7 wasn't just another big-block Chevy with updated technology. This was General Motors declaring war on the supercar establishment, and they brought a nuclear weapon to a knife fight. When this engine debuted in the 2006 Corvette Z06, it didn't just compete with European exotics, it embarrassed them. And it did it for about 1/10 the cost. To understand why the LS7 was such a shock to the system, we need to travel back to the early 2000s. The performance car world was dominated by complexity. More camshafts meant better breathing. More valves meant more power. Exotic materials were mandatory for high RPM operation. Variable valve timing was essential for making power across the rev range. Ferrari was using Formula One-derived technology in their road cars. BMW's M division was building high-strung inline-sixes and V8s that screamed to 8,000 RPM but needed valve adjustments every 15,000 miles. Even Porsche, masters of the simple air-cooled engine, had gone water-cooled and added layers of complexity to chase emissions and performance targets. American manufacturers weren't exactly setting the performance world on fire either. The C5 Corvette Z06 used the LS6 engine, a fantastic 5.7-liter V8, making 405 horsepower. Respectable, but not exotic. The Dodge Viper had displacement on its side with 8.3 liters, but it was crude, heavy, and inefficient. Ford's Mustang Cobra had supercharging, but still couldn't crack 400 horsepower reliably. The perception was clear. Americans could make torque, Europeans could make horsepower, and never the twain shall meet. But here's the thing about General Motors' small block V8 architecture. Since 1955, they'd been refining the same basic design. Not replacing it, not starting over, refining it. The LS family of engines, introduced in 1997, represented the 4th generation of this bloodline. They'd already proven you could make reliable power with pushrod simplicity. The LS6 in the previous Z06 was already punching above its weight class. But GM's engineers, specifically a team led by Dave Hill and Tom Wallace, had a different target in mind for the next Z06. They wanted to build a Corvette that could run with anything from Maranello, Stuttgart, or Sant'Agata Bolognese, not just in a straight line, but on a racetrack, in daily driving, at the dealer service department, everywhere. The challenge was monumental. They needed at least 500 horsepower to be taken seriously in supercar territory. It had to be naturally aspirated because that's what purists expected in a flagship sports car. It had to fit in the Corvette's engine bay without major modifications. It had to pass emissions regulations in all 50 states plus Europe. It had to be reliable enough for GM's warranty. It had to idle smoothly enough for your grandmother to drive to church. And here's the real kicker. It had to cost less than $15,000 to manufacture. So what was actually going wrong with existing approaches to making big, naturally aspirated power? Complexity was killing everyone. Ferrari's V12 engines used dual overhead cams, 4 valves per cylinder, variable valve timing, and exotic materials like titanium connecting rods. All that technology worked, but it created multiple failure points. More moving parts meant more friction. Complex valve trains meant sky-high maintenance costs. Exotic materials meant exotic manufacturing costs. The Europeans had painted themselves into a corner where making 500 horsepower naturally aspirated required space program levels of engineering. GM's solution was brilliantly counterintuitive. Instead of adding complexity, they'd remove it. Instead of shrieking to 9,000 RPM, they'd make their power by 6,500. Instead of exotic materials, they'd use racing-proven conventional ones. The LS7 would be the ultimate expression of the KISS principle. Keep it simple, stupid. The foundation was displacement. 427 cubic inches, or 7 liters for the metrically minded. That number wasn't random. Chevrolet's most legendary racing engines had been 427s. The L88, the ZL1, the Mystery Motor, all displaced 427 cubic inches. But this wasn't going to be some nostalgic throwback. This was cutting-edge engineering wrapped in classic American philosophy. There's no replacement for displacement. The block itself was a work of art disguised as a chunk of aluminum. GM used a deep skirt design with 6-bolt main caps, 4 vertical bolts, and 2 horizontal bolts per cap. This created a bottom end so strong that tuners would later push these engines past 1,000 horsepower without touching the rotating assembly. The cylinder walls used pressed-in iron liners rather than parent-bore aluminum. Old tech? Maybe. But it meant consistent bore dimensions even after hundreds of heat cycles. The deck height was raised compared to the standard LS engines, allowing for a longer stroke without compromising rod ratio. But the real genius was in the details nobody saw. The oil passages were sized for racing oil flow rates. The coolant passages were optimized using computational fluid dynamics to eliminate hot spots. The main bearing bulkheads were reinforced in exactly the places that would see stress at high RPM. Every unnecessary ounce was removed. The result was a bare block that weighed just 109 pounds but could handle twice its rated power without breaking a sweat. The rotating assembly was where GM spent their money. The crankshaft was forged from 4-140 steel, not billet, not exotic alloy, just good old American steel forged into submission. It was gun-drilled to reduce weight and knife-edged to reduce windage. The stroke was 4 inches exactly, working with a 4.125-inch bore to achieve that magic 427 cubic inches. The connecting rods were titanium, the only truly exotic material in the entire engine. But here's the brilliant part. They weren't titanium because GM was showing off. They were titanium because it was the only way to achieve the rod weight necessary for 7,000 RPM operation without compromising strength. Each rod weighed 464 grams, about 150 grams lighter than a comparable steel rod. That weight reduction meant less stress on the rod bolts at high RPM, which meant better reliability. The pistons were forged from 2618 aluminum alloy with a hyper-eutectic coating on the skirts. The compression ratio was 11.01, aggressive for a street engine, but conservative compared to the 12.1 or 13:1 ratios of contemporary European engines. This meant the LS7 could run on 91-octane pump gas all day long, while Ferrari owners were hunting for 100-octane race fuel. The ring pack used a 1.2-meter compression ring, narrower than even most race engines of the era. Less ring tension meant less friction, which meant more power and better fuel economy. Now here's where GM's old-school approach really shined. The valve train was pushrod operated, 2 valves per cylinder, no variable timing, no variable lift, no fancy electronics. The automotive press called it antiquated. GM's engineers called it perfect. The camshaft was a steel billet hydraulic roller with 0.591-inch lift on both intake and exhaust. The duration was 211 degrees intake, 230 degrees exhaust at 0.052-inch lift. Those numbers might not mean much to non-engine builders, but here's what matters. This was an incredibly aggressive profile for a hydraulic cam, yet it idled at 600 RPM like a stock Suburban. The rocker arms were investment cast with a 1.81 ratio, higher than the standard 1.71 of most LS engines. This gave more valve lift without requiring a wilder camshaft. The valve springs were ovate beehive designs from Pack Racing. That beehive shape meant less mass at the top of the spring, which meant higher RPM capability without valve float. The push rods were 7.4 inches long, one piece, 0.080-inch wall thickness. Again, nothing exotic, just properly engineered conventional components. Let that sink in for a moment. Ferrari was using pneumatic valve springs in their Enzo to achieve 8,000 RPM. BMW was using double Vanos variable timing to make power across the rev range. Mercedes was using 4 valves per cylinder with dual overhead cams. GM said, "Watch this," and made more specific power with push rods and 2 valves per cylinder. The cylinder heads were CNC ported from the factory, not hand-ported by Italian craftsmen, but cut by robots to aerospace tolerances. The intake ports flowed 375 CFM at 0.600-inch lift. The exhaust ports flowed 263 CFM. For comparison, a NASCAR Sprint Cup head of the same era flowed about 400 CFM on the intake. This was basically race engine airflow in a street engine. The combustion chambers were 70 cc heart-shaped, with the spark plug positioned for optimal flame propagation. The valve sizes were massive: 2 20-inch hollow stem titanium intakes, 1.61-inch hollow stem Inconel exhausts. Those materials weren't chosen for bragging rights. The titanium saved 40% of the valve weight, crucial for high RPM operation, while the Inconel could handle exhaust temperatures that would melt conventional steel. The intake manifold was a lost foam cast aluminum piece that looked like it came from a Trans Am race car because, essentially, it did. The runners were sized for peak power at 6,500 RPM with no consideration for low-end torque. Why? Because even with that racing-oriented intake, the LS7 still made 470 lb-ft of torque at 4,800 RPM. The throttle body was a 90mm drive-by-wire unit, about the size of a coffee can. The fuel injectors were 65 lb-hr units, massive by street car standards, but necessary to feed 427 cubic inches at full throttle. But here's where it gets interesting. The dry sump oiling system wasn't some afterthought or racing upgrade. It was engineered from the beginning as an integral part of the engine's architecture. The system used a 2-stage pump that could move 25 gallons per minute at full pressure. The external oil tank held 10.5 quarts, including what was in the engine. This wasn't just about preventing oil starvation during high-G cornering. The dry sump system meant the engine could be mounted lower in the chassis, improving the center of gravity. It meant better oil temperature control through the external cooler. It meant consistent oil pressure, even at sustained 7,000 RPM operation. When final assembly came together at GM's Performance Build Center in Wixom, Michigan, each LS7 was hand-built by a single technician. Not because robots couldn't do it, but because GM wanted that human touch, that pride of ownership. Each builder signed their engine, literally putting their name on their work. The engines were hot-tested before shipping, not just run on a stand, but actually put through heat cycles and load tests. If an engine didn't make its rated power perfectly, it didn't ship. The result? 505 horsepower at 6,300 RPM, 470 lb-ft of torque at 4,800 RPM. But those peak numbers only told part of the story. The LS7 made over 400 lb-ft of torque, From 2,000 RPM to 6,000 RPM, it made over 450 horsepower from 5,500 RPM to redline. This wasn't some peaky race engine that needed to be kept on boil. This was a sledgehammer that happened to also be a scalpel. In the 2006 Corvette Z06, the LS7 transformed a car that weighed 3,130 pounds into a legitimate supercar killer. 0 to 60 happened in 3.5 seconds. The quarter mile disappeared in 11.5 seconds at 127 mph. Top speed was 198 mph. Those numbers didn't just compete with European exotics, they beat many of them. A Ferrari F430 with its 4.3-liter V8. Making 483 horsepower, slower to 60, slower through the quarter, lower top speed. The Lamborghini Gallardo with its 5.0-liter V10. Dead even to 60, but the Z06 pulled away after that. The Porsche 911 Turbo needed forced induction to keep up with the naturally aspirated LS7, but raw performance was only part of the equation. The real shock came at the racetrack. Car and driver took a Z06 to Virginia International Raceway and lapped it in 2:51.8. That was faster than a Ferrari Enzo, a car costing 10 times as much with 146 more horsepower. Road and Track ran a Z06 around their test track faster than a Ford GT, Porsche Carrera GT, and Mercedes McLaren SLR. The Z06 wasn't just keeping up with supercars, it was embarrassing them. The automotive press couldn't believe what they were seeing. Here was an American car with a pushrod engine, leaf springs, and a fiberglass body running circles around Europe's finest. The Germans called it crude, but couldn't explain why it was faster. The Italians called it unsophisticated, but couldn't match its lap times. The British were perhaps the most honest. Jeremy Clarkson, never one to praise American cars, called the Z06 absolutely phenomenal and admitted it could keep up with anything from Europe. Track testing revealed something else remarkable. The LS7 just wouldn't break. Journalists ran Z06 flat out for hours in desert heat, subjected them to repeated launch control starts, did back-to-back track sessions that would cook most engines. The LS7 barely noticed. Oil temperatures stayed reasonable thanks to the dry sump system. Coolant temperatures remained stable even in 120-degree ambient heat. The hydraulic lifters never pumped up. The valve springs never floated. While Ferrari owners were scheduling valve adjustments and BMW M owners were replacing rod bearings, LS7 owners were just changing oil. The racing world took notice immediately. The LS7 became the basis for GM's factory racing engines in the American Le Mans Series. With minor modifications, different cam, higher compression, race exhaust, these engines made 590 horsepower and could run for 24 hours straight at tracks like Sebring and Le Mans. The Corvette racing team won championship after championship with LS7-based power. These weren't heavily modified race engines. They were basically production LS7s with safety equipment and different tuning. In 2007, the LS7 found its way into the fifth-generation Camaro Z28. This wasn't supposed to happen. The Camaro was too heavy, too practical for such an exotic engine. But GM's engineers made it work, and the result was perhaps even more impressive than the Z06. Here was a 3,800-pound muscle car that could lap the Nürburgring in 7:37, faster than a Lamborghini Murcielago LP640. The Z28 wasn't just fast. It proved the LS7 could perform in any chassis, at any weight, in any application. The aftermarket went absolutely insane for the LS7. Tuners discovered that with heads and cam work, these engines could make 700 naturally aspirated horsepower while maintaining street manners. Add forced induction, and 1,000 horsepower was routine. 500 horsepower was achievable. 2,000 horsepower was possible if you were brave enough. And here's the truly remarkable part: the bottom end could handle it. Those forged internals, that bulletproof block, the titanium rods, they were so overbuilt from the factory that doubling or tripling the power output rarely required internal modifications. Catech Performance, one of GM's development partners, created the Street Attack 427, an LS7 variant making 700 horsepower naturally aspirated with a warranty. Lingenfelter Performance Engineering built LS7s making 660 horsepower that could pass emissions testing in California. These weren't fragile race engines. They were daily drivable monsters that happened to make more power than most dedicated race cars. So what was the secret? How did GM build an engine that made Ferrari power for Chevrolet money? The answer was elegant simplicity combined with relentless optimization. Every decision prioritized function over form. 2 valves per cylinder meant larger valves could fit, which meant better flow at high lift. Pushrods meant a lower center of gravity and more compact external dimensions. Fixed valve timing meant one less system to fail. The large displacement meant low stress per cylinder, which meant longevity. But the real genius was in what GM didn't do. They didn't chase specifications for bragging rights. They didn't add technology for technology's sake. They didn't build an engine that needed a laptop to tune or a specialist to service. They built an engine that any competent mechanic could work on with normal tools. Replacement parts were available at any Chevy dealer. You could buy a complete LS7 crate engine from Chevrolet Performance for about $15,000, less than what Ferrari charged for a clutch replacement. The financial mathematics were staggering. A Ferrari F430 engine rebuild cost approximately $40,000 and was recommended every 30,000 miles. An LS7 could go 100,000 miles with just oil changes and maybe a set of valve springs. The Ferrari required special tools, special fluids, special everything. The LS7 used the same oil filter as a Silverado pickup truck. When something did break, which was rare, parts were cheap and readily available. A set of LS7 heads cost $2,000. Ferrari heads? Try $15,000 if you could even find them. The deeper you looked into the LS7's design, the more brilliant it became. The compression ratio of 11.0.1 was high enough for power, but low enough for pump gas. The bore spacing of 4.4 inches was the same as every small block Chevy since 1955, meaning decades of development knowledge applied. The 2-bolt accessory drive meant no complex serpentine belt arrangements. The coil-near-plug ignition meant no distributor to fail, but also no complex coil-on-plug system to diagnose. Think about that for a second. Ferrari needed 12 cylinders to make 651 horsepower in the Enzo. That's 54 horsepower that American engineering could compete with anyone when properly executed. It showed that traditional hot rod philosophy, bigger displacement, simpler design, bulletproof construction, still had merit in the modern age. It demonstrated that you didn't need to be wealthy to own genuinely exotic performance. A used LS7 could be swapped into almost anything. Mechanics were putting them in everything from 1960s Camaros to Mazda RX-7s to kit cars to boats. The LS7 also changed how people thought about engine swaps. Previously, if you wanted 500-plus naturally aspirated horsepower in your project car, you were looking at complex builds, exotic imports, or highly stressed engines that needed constant attention. The LS7 offered supercar power with pickup truck reliability. It would idle in traffic, pass emissions, get decent fuel economy, and then rip off quarter-mile passes all day without complaint. Racing sanctioning bodies had to rewrite their rules because of the LS7. It was too good, too reliable, too powerful for existing class structures. In SCCA competition, LS7 powered cars were dominating so thoroughly that displacement-based penalties had to be introduced. In drag racing, the LS7 became the default choice for anyone wanting big naturally aspirated power without the complexity of a big block. Road racers loved that it could run flat out for hours without overheating or losing power. The engineering community took notice too. The LS7 won International Engine of the Year in the 3 to 4 liter category, competing against engines with half its displacement but twice the complexity. Engineers from other manufacturers admitted privately that GM had achieved something special. The LS7 proved that American engineers could match anyone for specific output while maintaining their traditional advantages in durability and cost. But perhaps the most impressive aspect was longevity. As I write this, the oldest LS7 engines are approaching 20 years of service. Many have over 100,000 miles. Some have been tracked extensively. Others have been modified beyond recognition. And yet, catastrophic failures remain remarkably rare. The forums aren't full of stories about windowed blocks or spun bearings. They're full of people asking if 150,000 miles is too many for a used LS7. The answer, remarkably, is usually no. The LS7 forced a recognition that would have seemed impossible in 2005. Pushrod engines weren't obsolete. In fact, for certain applications, they were superior. The packaging advantages, the lower center of gravity, the simplicity, the torque curve, all of it mattered in real-world performance. While others were adding turbochargers and hybrid systems to chase efficiency and power, GM had shown that proper engineering of conventional technology could achieve remarkable results. Consider the modern context. Today's supercars are increasingly turbocharged, electrified, and computerized. A new Ferrari 296 GTB makes 819 horsepower from a twin-turbo V6 with electric assistance. It's incredibly fast, incredibly complex, and incredibly expensive. But is it more impressive than the LS7 making 505 horsepower from natural aspiration with technology any shade tree mechanic can understand? Is it a greater engineering achievement or just a more complicated one? The LS7 represented something pure, something that's increasingly rare in modern automotive engineering. It was uncompromised in its mission to make big, reliable, naturally aspirated power. It didn't care about downsizing trends or turbocharging or electrification. It was the ultimate expression of traditional American V8 philosophy executed with modern precision. It proved that sometimes the old ways, properly refined, are still the best ways. When production ended in 2015, GM had built approximately 15,000 LS7 engines. Not a huge number, but each one was special. Each one carried the signature of its builder. Each one represented a high-water mark in naturally aspirated V8 development. Values for LS7-equipped vehicles have done nothing but climb since production ended. Clean Z06 Corvettes are becoming collectible. Camaro Z28s are already trading above their original sticker prices. Crate LS7s, when you can find them, sell for more than they cost new. The LS7's influence extends far beyond its production run. It proved that there was still a market for high-displacement, naturally aspirated engines in an era of downsizing. It influenced the development of the LT4, LT5, and even the new Z06's LT6 flat-plane crank V8. It showed that customers would pay premium prices for premium performance, even from a domestic manufacturer. It demonstrated that reliability and performance weren't mutually exclusive. Modern engineers still study the LS7. How did GM get such good airflow from two-valve heads? How did they achieve such high RPM from pushrods? How did they make it so reliable while being so powerful? The answers are all there in the design. No secrets, no magic, just relentless attention to detail and a clear vision of what the engine needed to be. Looking at today's automotive landscape, the LS7 feels like it came from another era, an era when engineers could build engines without worrying about corporate average fuel economy standards, an era when naturally aspirated power was still king, an era when simplicity was valued over complexity. That era is gone, replaced by turbochargers, direct injection, and 48-volt mild hybrid systems. But the LS7 stands as a monument to what was possible when engineers were told to build the best naturally aspirated V8 they could, cost be damned. And then they did it for less than anyone thought possible. The legacy of the LS7 isn't just about horsepower or lap times or drag strip victories. It's about proving that American engineering, when properly focused and funded, could build world-class engines. It's about demonstrating that traditional technology, perfectly executed, could outperform cutting-edge complexity. It's about showing that you didn't need to spend Ferrari money to get Ferrari performance. The LS7 made exotic performance accessible to the average enthusiast, and that democratization of speed changed the performance car landscape forever. In the end, the LS7 was more than just an engine. It was a statement that said Pushrod V8s weren't dead, that American engineering could compete with anyone, that simplicity, when perfectly executed, beats complexity every time, that you could build a 500 horsepower naturally aspirated engine that your neighbor could service in his garage. That statement resonated around the world, and its echoes are still being felt today in every performance car that prioritizes function over flash, reliability over complexity, and results over rhetoric. The LS7 didn't just outsmart every European supercar, it exposed the fundamental flaw in their approach. While they were adding complexity to chase incremental gains, GM proved you could achieve more with less. While they were building engines that required specialists to maintain, GM built one that any competent mechanic could service. While they were charging six figures for their motors, GM was selling the same performance for the price of a nice motorcycle. The LS7 wasn't just better, it was better in every way that actually mattered to the people who drove them. What's your dream LS7 swap project? Drop a comment below and let me know what you'd stuff this legendary engine into. And if you enjoyed this deep dive into one of America's greatest engines, make sure to subscribe, because we're just getting started with the stories of engineering marvels that change the game.